Alright, let's go. Number 10. The Impossible Early Galaxies. Evolab and his team at Swinburne University of Technology were not hunting for a crisis. They were doing catalog work, sorting through the first NIRCam images from the Cosmic Evolution Early Release Science Survey, a 40-square arc-minute patch of sky, flagging red objects worth a spectroscopic follow-up. Routine triage. The kind of task you hand to a postdoc on a Tuesday. The standard model has a rule about this era. Structure builds from the bottom up. Small clumps of dark matter merge into larger ones, gas falls in, cools, and forms stars. It is slow. 600 million years after the Big Bang, you should be looking at ragged, half-assembled objects. 1 billion solar masses of stars at the absolute outside. 6 of the objects were not ragged. They were compact, they were red, and when the team fitted the photometry, the stellar masses came back at 10 billion solar masses. One fitted at 100 billion. That is a fully grown Milky Way, sitting in the dark at cosmic dawn. The paper is Lab and Colleagues, Nature, Volume 616, pages 266 to 269, published in 2023. A population of red candidate massive galaxies 600 million years after the Big Bang. Michael Boylan Colchin at the University of Texas at Austin ran the Arithmetic in Nature Astronomy the same year, Volume 7, page 731. His conclusion was narrower and worse. To assemble those galaxies, you would need more baryons than the dark matter halos of that epoch are permitted to contain. Every exit has been tried. Maybe the photometric redshifts were wrong and these are dusty galaxies much closer to us. Spectroscopy has since confirmed several of them sitting exactly where they appeared to be. Maybe the masses were inflated by an accreting black hole, contributing light that was mistaken for starlight. Dale Kuchevsky confirmed at least one as an active galactic nucleus, which rescues that object and leaves the rest standing. Maybe the first stars formed with a different mass distribution, producing more light per unit of mass. Nobody has demonstrated that independently. Maybe star formation was simply more efficient early on. Catherine Chorowski's 2024 analysis found that even under that assumption, the extreme cases demand converting roughly 50% of all available gas into stars. The local average is closer to 5. Every atom of calcium in your bones was manufactured inside a star, and the schedule for when those stars became possible is the schedule in every textbook. If galaxies assembled this fast, the opening chapter of Where Your Body Came From is wrong by an order of magnitude. 4 years of follow-up, and no one can say with confidence what these objects actually are. The problem gets sharper when you stop looking at populations and look at one galaxy. Number 9. The record that should not have been breakable. Emma Curtis Lake at the University of Hertfordshire was working the confirmation end of the pipeline. The JWST Advanced Deep Extragalactic Survey had produced a list of color-selected candidates from deep imaging around the Hubble Ultra Deep Field. Her job was unglamorous and essential. Point near spec at 4 of them for 28 hours and find out which candidates survived contact with the spectrum. Photometric candidates usually do not survive. The color selection technique works by spotting, where hydrogen absorption cuts off a galaxy's light, the Lyman break. But dusty red galaxies at moderate distance can counterfeit that signature almost perfectly. The historical failure rate is substantial. Hubble's own record holder, GNZ11, had spent years under suspicion. All 4 survived. The most distant, JADES GSZ 13.0, came back at Redshift 13.2. Curtis Lake and colleagues published this in Nature Astronomy, Volume 7, pages 622 to 632. In 2023, spectroscopic confirmation of 4 metal-poor galaxies between Redshift 10.3 and 13.2. JADES GSZ 13.0 has a stellar mass near 90 million solar masses and existed roughly 320 to 400 million years after the Big Bang. In 2024, Stefano Carniani's team broke that with JADES GSZ 14.0 at Redshift 14.18 under 300 million years, 2% of the current age of the universe. Its half-light radius is 260 parsecs. It is luminous, and it is tiny. The objections were made and answered in order. contamination from a foreground object ruled out by the shape of the damping wing in the spectrum. A lower redshift solution with unusually strong emission lines modeled and rejected by the photometry. An error in the wavelength calibration checked against the instrument's known behavior. A statistical fluke in a small survey volume, JADES Data Release 5 lists 19 further candidates above redshift 14 in the same two fields. You were watching light that left its source before the first generation of stars had finished dying. Not a reconstruction. Not a simulation. Photons that have been in flight for 13.4 billion years, arriving at a mirror in the cold, showing something that the models say had not had time to exist. If the earliest thing we can see is already too early, how do we know where the beginning is? Size is one kind of impossibility. Structure is another. Number 8. The Big Wheel. Weichin Wang, a postdoctoral researcher at the University of Milano-Bicocca, was studying a dense node of the cosmic web at redshift 3 and found a large spiral galaxy sitting in his field of view. His first assumption was that it was junk data, an interloper from much later in cosmic history that happened to fall in the frame. It looked wrong for the epoch, so he treated it as a distraction and continued with the actual project. Disk galaxies are supposed to be fragile and late. Building an ordered rotating disk requires a long stretch of calm, no major mergers, no violent gas inflows, because collisions destroy disks and turn them into shapeless blobs. The early universe is the most violent environment there has ever been. Large, settled spirals are the product of billions of years of quiet. The interloper was not an interloper. Hydrogen alpha spectroscopy with NIRSpec confirmed it was rotating at redshift 3 when the universe was about 2 billion years old. Wang and colleagues published it in Nature Astronomy in 2025. A giant disk galaxy 2 billion years after the Big Bang. Its stellar disk extends at least 30 kiloparsecs. Its half-light radius is 9.6 kiloparsecs along the major axis. It rotates at roughly 300 kilometers per second, placing it at the high end of the Tully-Fisher relation. It is 3 times the size of comparable galaxies of its epoch. According to the team's own models, the odds of finding an object like it in that survey volume were under 2%. Explanations were assembled. A recent merger inflating the apparent size, the kinematics show an ordered disk, not a wreck. A chance alignment of 2 galaxies, spectroscopy places them at the same redshift. Contamination by an active nucleus brightening the center, Chandra did detect an ang there which changes the light budget and not the rotation curve. The surviving explanation is environmental. The big wheel sits inside the MQN-01 structure, one of the densest known overdensities at that redshift. It was fed. Chuck Steidel at Caltech described it as the child who ate everyone else's breakfast. You live inside a disk galaxy. The spiral arm outside your window is supposed to have taken most of cosmic history to settle into shape. Something built one in 15% of that time. If the calm was never required, what exactly is our galaxy's age measuring? Some early galaxies formed too fast. One of them stopped. Number 7. The Galaxy That Died Young. Tobias Lucer at the Kavli Institute for Cosmology in Cambridge was working through NIRSpec spectra of Lyman break galaxies from the JADES program, standard characterization work, measuring redshifts and star formation rates for objects in the epoch of reionization. The expectation was straightforward. These are infant galaxies in a gas-rich universe, and infant galaxies in a gas-rich universe make stars. Star formation shuts down late. In the modern universe, quenching happens to massive galaxies that have exhausted their gas, or had it heated and expelled by a central black hole, or been stripped by a cluster environment. It takes billions of years and requires machinery that should not yet exist. At 700 million years after the Big Bang, the phrase dead galaxy is a category error. The spectrum of JADES GS Z701Q had a Balmer break and no nebular emission lines at all. Not weak lines. None. Lucer and colleagues published it in Nature in March 2024, a recently quenched galaxy 700 million years after the Big Bang. Formal designation JADES GS plus 53.15508, 27.80178, redshift 7.29, stellar mass between 400 million and 600 million solar masses, half-light radius roughly 200 parsecs. The reconstructed history shows an intense burst lasting somewhere between 30 and 90 million years, followed by a shutdown that occurred 10 to 20 million years before the light we are receiving left the galaxy. Astronomically speaking, we caught it in the act. Nothing in the standard toolkit fits. A supermassive black hole blowing the gas out, no AND signature in the spectrum. And the galaxy is too small to host the required engine. Environmental stripping, it is not in a cluster, clusters do not exist yet. Simple gas exhaustion, plausible, except the surrounding universe is saturated with gas that should fall back in. Supernova feedback from the burst itself, the leading candidate, and it requires feedback far more violent than any local analog. Francesco Eugenio's own team allow that the galaxy may only be temporarily quenched and may reignite. That is not a solution. That is an admission that the shutdown is not understood well enough to know whether it is permanent. The sun that keeps your body at 37 degrees exists because gas kept collapsing for billions of years. Something in the early universe turned that process off in less time than mammals have existed on Earth. Was it dead? Or is it still holding its breath? Dead galaxies are strange. What sits at the center of them is stranger. Number 6, UHZ-1. Cos Bogdan at the Center for Astrophysics, Harvard and Smithsonian, was doing something almost mundane, pointing the Chandra X-ray Observatory at a galaxy cluster called Abell 2744, 3.5 billion light-years away, and using its gravity as a magnifying lens to look at whatever happened to lie behind it. Gravitational lensing is a free telescope. You take what it gives you. Supermassive black holes are supposed to require time. If you start with the corpse of a massive star, 10 to 100 solar masses, and feed it at the physical maximum rate that radiation pressure permits, reaching millions of solar masses takes hundreds of millions of years of uninterrupted, perfectly efficient accretion. Nothing accretes uninterrupted. Behind the cluster, JWST found a galaxy. 2 weeks of Chandra observation found superheated X-ray emitting gas at the center of it. A growing supermassive black hole, 470 million years after the Big Bang. The discovery paper is Bogdan and colleagues in Nature Astronomy, 2023, evidence for a heavy seed origin of early supermassive black holes from a redshift 10 X-ray quasar. The interpretation paper is Priyamvada Natarajan and colleagues the Astrophysical Journal Letters, volume 960, number 1, published December 2023. UHZ-1 sits at redshift 10.1. The X-ray source is a Compton-thick quasar with a bolometric luminosity around 5 times 10 to the 45 ergs per second, implying a black hole mass near 40 million solar masses. The detail that matters most, the JWST data give a stellar mass for the entire host galaxy that is comparable to the mass of the black hole inside it. Light seed formation cannot produce this. The arithmetic fails by hundreds of millions of years. Sustained super Eddington accretion could, in principle, but no mechanism keeps it stable that long. A merger of many smaller black holes requires a population of smaller black holes nobody has found. The surviving explanation is direct collapse, an enormous primordial gas cloud skipping the star formation stage entirely and falling straight into a black hole of perhaps 100,000 solar masses. Natarajan predicted objects exactly like this 6 years before UHZ-1 was found. Being right does not mean the mechanism has been observed. There is a black hole at the center of the galaxy you live in, and the standard account of how it got there begins with a dying star. UHZ-1 suggests the account begins somewhere else entirely. If black holes came first, what were galaxies built around? UHZ-1 is one object. The pattern is the problem. Number 5. The overweight black holes. Roberto Maialino's group at Cambridge was performing an inventory. JWST's NIRSpec had produced spectra for large numbers of faint high redshift sources, and the task was to identify which ones showed the broad emission lines that betray gas whipping around an accreting black hole. Census work. Counting, there is a relation in the local universe that has held for decades. A galaxy's central black hole carries roughly 0.1% of the mass of the surrounding stellar bulge. It holds across 5 orders of magnitude. It is one of the most reliable empirical laws in extragalactic astronomy, and it implies that black holes and their host galaxies grow together, regulating one another. At high redshift, the relation breaks, not by a little. Fabio Piccucci and colleagues published the quantitative statement in the Astrophysical Journal Letters, volume 957. In 2023, JWST and JADES active galaxies at redshift 4 to 7 violate the local black hole to stellar mass relation at more than 3 sigma. In Nature, volume 627, pages 59 to 63, published in 2024, Maialino's team reported that GNZ11, 440 million years after the Big Bang, hosts a black hole of about 1.6 million solar masses, accreting at roughly 5 times the Eddington limit, with an outflow moving at 800 to 1,000 kilometers per second. Their JADES survey paper cataloged the wider population, black holes at redshift 4 to 11, that are, in their own summary, merging, tiny, poor but mighty. Selection bias is the obvious defense. We see the brightest, and the brightest are overweight. Piccucci's team modeled it. The offset survives. Overestimated black hole masses from applying local calibrations to alien conditions, a real concern. And the direction of the error is not established. Underestimated stellar masses hidden behind dust, Alvarez-Mezquez's 2025 MIRI analysis of GNZ11 pushes in the opposite direction, questioning whether the black hole is there at all in the mass claimed. The relation that ties black holes to galaxies is the reason we believe the two co-evolve. In the early universe, that link does not hold, which means it is not a law. It is a habit the universe developed later. If the rule was not always the rule, when did it start and what enforces it? The most numerous anomaly in the JWST catalog does not even have a proper name. Number 4. The Little Red Dots. Jorrit Matthey, then at ETH Zurich and now at the Institute of Science and Technology Austria, was working with the Eiger and Fresco surveys, using JWST's GRISM mode to catch emission lines from galaxies at redshift around 5. The objects kept appearing in the images, extremely compact, extremely red, and small enough to be unresolved. Point sources. He gave them the plainest possible name. A point source at cosmological distance is either a quasar or a star. Both categories come with obligations. Quasars emit X-rays because gas falling into a black hole heats to millions of degrees. Dust-reddened quasars have characteristic infrared excess. Compact galaxies have measurable extent. The little red dots met none of these obligations. Matthey and colleagues published the defining paper in the Astrophysical Journal, volume 963, page 129, on 10 March 2024. The population appears roughly 600 million years after the Big Bang and disappears from the record by about 1.6 billion years. By 2025, the catalog had reached 341 objects. Their spectra show a V-shape, blue in the ultraviolet, steeply red in the optical, and broad hydrogen lines implying gas at extreme velocities. If those line widths are read as orbital motion, the implied black holes are enormously overweight relative to their hosts, and the implied number density exceeds the extrapolated quasar luminosity function by more than an order of magnitude. Then the explanations began failing in sequence. Dusty active nuclei. The X-rays are absent and the radio emission is absent. Extremely dense star clusters. Josephine Baggins' work showed the stellar densities required are implausible. Ordinary massive galaxies, they are far too compact. This one is closing. In January 2026, a Nature paper by Rusakov and colleagues argued that the broad lines are widened by electron scattering in a dense ionized cocoon, meaning the black holes are roughly 100 times lighter than first estimated. The black hole star model. A study published on 29 July 2026 in the Astrophysical Journal pushed further toward dust-obscured black holes in rapid growth. 4 years of a population that fit nothing, resolving into something. For 4 years, the most numerous new object in the deep sky had no category. That is what a genuine gap in a working theory looks like from the inside. If it took 4 years and hundreds of papers to name these, what else is sitting unnamed in the archive? Chemistry has been keeping worse secrets than morphology. Number 3. The oxygen that should not exist. 2 teams, one led by Stefano Carniani at the Scuola Normale Superiore in Pisa, one by Sander Schaus at Leiden Observatory, pointed ALMA at JADES GS Z14O. The intent was a distance refinement. Find the oxygen fine structure line at 88 microns, use it to pin the redshift precisely, and improve the calibration of everything else. Neither team expected the line to be strong. Oxygen has a manufacturing schedule. It does not come from the Big Bang, which produced hydrogen, helium, and a trace of lithium. Oxygen is forged in massive stars and released when they die. To have oxygen distributed through a galaxy's gas, you need a generation of stars to form, live, and explode. Under 300 million years, you should be looking at close to pristine primordial gas. Both teams found the line. Independently, clearly, Carniani and colleagues published in Astronomy and Astrophysics on 20 March 2025 the eventful life of a luminous galaxy at Redshift 14, metal enrichment, feedback, and low gas fraction. Schaus and colleagues published in the Astrophysical Journal the same day. The galaxy sits at Redshift 141793. The oxygen detection fixes its distance to an uncertainty of 0.0005%. The heavy element abundance is roughly 10 times what models predicted for that epoch. Gas phase metallicity is estimated between 5 and 20% of solar. Schaus described it as finding an adolescent where you expected to find babies. The ordinary escapes do not apply. A foreground contaminant producing the line, the frequency matches the JWST redshift to 5 decimal places. An instrumental artifact, 2 teams, independent reductions, same result. A single unusually enriched object, Jorge Zavala's team found the same 88 micron line in GHC2 at redshift 12.33. The remaining requirement is that at least 2 full stellar generations lived and died inside this galaxy before the universe was 300 million years old. Roughly 65% of your body's mass is oxygen. Every one of those atoms was made in a star. The earliest galaxy we can see was already making them faster than our models permit. How many generations of stars have already come and gone before the earliest thing we can detect? The deepest problem is not what JWST found. It is what it failed to settle. Number 2. The tension that JWST was supposed to end. Wendy Friedman at the University of Chicago went into this expecting resolution. The Hubble constant, the expansion rate of the universe, disagreed with itself. Measurements from the cosmic microwave background gave one number. Measurements from nearby stars gave a higher one. The dominant suspicion was crowding. Cepheid variable stars in distant galaxies are blurred together with neighbors in Hubble's images, contaminating their brightness. JWST has 4 times Hubble's angular resolution. Point it at the same stars, and the contamination should vanish. If the tension were a measurement artifact, sharper images would close it. That is the entire logic of the experiment. The images got sharper. The disagreement did not go away. On 13 March 2024, Friedman's Chicago Carnegie Hubble program unblinded 3 independent distance measurements to 11 galaxies. Cepheids, tip of the red giant branch, and the J-band asymptotic giant branch method. TIRGB gave 69.85. Cepheids gave 72.05, with the value sliding between 69 and 73, depending on assumptions. Combined, Friedman's 2025 analysis reported 69.96 plus or minus 1.53 kilometers per second per megaparsec. Adam Rees and the Shrews team, using an extended set of JWST calibrator hosts, reported 72.6 plus or minus 2.0. The Shrews distance ladder value stands at 73.17 plus or minus 0.86, against a Planck cosmic microwave background prediction of 67.4 plus or minus 0. 5. A discrepancy exceeding 5 sigma. Crowding was tested and largely eliminated as the dominant systematic. Cepheid metallicity corrections have been revisited repeatedly without closing the gap. Sample size objections were raised by Rees and answered by Friedman. Xiang Li's reanalysis showed that applying Friedman's Churg-B distances to the complete supernova sample pushes the number back up. Dan Skolnick told the American Astronomical Society in January 2025 that the tension had become a crisis. Friedman has not conceded. Neither has Ries. The age of the universe is a division problem, and this is the denominator. If the higher value holds, the universe is younger than some of the stars we have already dated. The number that tells you how much time has existed is not known. Two careful teams, the same telescope, the same stars, and no agreement on how old anything is. The last one is the simplest thing on this list, which is exactly why it is difficult. Number 1. The preferred direction. Lior Shamir, a computer scientist at Kansas State University, was not doing cosmology in the usual sense. He was running an image analysis algorithm, the kind of symmetric, automated classifier built to avoid human bias over galaxies in the JADES deep field. The measurement is almost trivially simple, for each spiral clear enough to resolve. Determine which way it wins. There is no mechanism in cosmology that would produce a preference. The universe is assumed isotropic, the same in all directions, and galaxy spin axes should be randomly oriented. Across a large sample, clockwise and counterclockwise should split 50-50 within noise. This is not a prediction so much as a foundational assumption underneath every cosmological model in use. Out of 263 galaxies with clearly identifiable spin, 158 rotated one way and 105 the other. Shamir published it in Monthly Notices of the Royal Astronomical Society, Volume 538, Issue 1, pages 76 to 91, on 17 February 2025. The excess is roughly 50% at a statistical significance near 3.4 sigma. The JADES field lies close to the southern galactic pole, which matters, because earlier ground-based work, including analyses of more than 1 million galaxies in the DESI Legacy Survey, showed a smaller signal in the same direction. Shamir's own earlier papers argue the asymmetry grows with redshift. The candidate explanations are genuinely uncomfortable. Observational bias from the Milky Way's own rotation, where Doppler boosting makes counter-rotating galaxies marginally brighter and therefore over-selected, which would mean every galaxy survey ever conducted carries an uncorrected systematic. A real large-scale anisotropy, meaning the universe has a preferred axis and isotropy is false. Or the black hole cosmology reading, in which a parent black hole's spin is inherited by the universe inside it, a fringe idea that Shamir's paper mentions and does not endorse. And a substantial literature, Aye and Shugai, Land, Hayes, Patel, and Desmond, has found the distribution to be random. This is contested. It should be treated as contested. You are standing on a planet orbiting a star inside a spinning disk, and the direction it spins may not be arbitrary. It may be a fossil of something the universe decided before there were galaxies. If the sky has a preferred direction, what chose it? The universe is not confused. We are. Look at what these 10 have in common. Not one of them lives at the edge of knowledge. In some exotic corner nobody has tested. They sit at the center in structure formation, in stellar nucleosynthesis, in the expansion rate, and the assumption of isotropy. These are our most confirmed theories, and the anomalies are inside them. We built a telescope to see the beginning, and it showed us that our clock, our chemistry, and our sense of direction were all approximations. The instrument worked perfectly. That is the problem. If you want to see more videos like this, click the video on screen now.